Okay, we have only 3 weeks remaining. Alright, so we have today we'll cover chapter 10 by Alexandre and myself. Discussion will be fine. All the files already in the cut. Good. And on Wednesday we will have a chapter 11 and final presentation. No question schedule. Okay, then Alexandre.
Okay, hello everyone. Today I'll be covering chapter 10. We're still studying this book, and here we are in the book, so nearly at the end. So here are the contents of this lecture. Let's go. So what we'll do today is have a more detailed look at the design and actual implementation of a feature-based modeling system, and specifically what data structure can we use. So we will see a data structure based on frames in object-oriented programming, and this data structure based on frames will be used on these parts of the CAD system. So basic representation methods, feature definition, and feature geometry definition. So first, what is a frame? A frame is a data structure that consists of a sequence of attributes, also called slots and values. It's a popular Lisp programming technique for knowledge representation, and it's used for creating complex data structure. And we work with frames in the object-oriented programming. So if you don't know object-oriented programming, it's a solution to have to defeat complex software problems. It uses classes, which are blueprints for creating objects and providing the functions these objects should have, etc. And very important, classes are organized into hierarchy, so there is inheritance of information. You have classes, subclasses that inherit functions and information from these parent classes. So what does it look like? Here we have an instance frame to represent an instance of an object. So if you have an internal keyway slot 11, and that's shown on the left, you can see that we define some dimensions, orientation positions, the surface positions, etc. Also, frames can represent classes. For instance, if we have a definition of a class called internal keyway slot, and we have a few functions. With this line, we define what existing items should belong to this class. For instance, we have the default values of the object of this class should have, etc. Also, we have inheritance. We can write here that the class internal slot is a subclass of a slot feature, but we can do it also the other way. We can say that all these classes are a subclass of internal slot. And we can also use inheritance on surfaces, not only on features. So if we want to make an instance of an object in the frame programming language, typically you would say this. So you will see the line that says make an instance of internal keyway slot. So you call the class of the object you want. But you can also precise like the name you want for this object you create, And if you want to override the default values you've input for the class, you can say what dimensions you actually want. Next, we know that in a programming language we also have functions. Here they are called methods, and they are very powerful, as expected. For instance, if we want to create this block with a slot in it, we may want to create the block first. This is the code for it, and we may want to have a very useful function that creates a slot in that block. So you precise the block, which side of the block you want the feature to be, the slot to be in, and then the name of the actual feature instance. But with all these classes, subclasses, etc., it can get quite messy with the names. So of course there has been studies on taxonomy. So the goal is to simplify this tree of classes and encourage on the extension. And what's traditionally for CAD systems is that we have under the feature main class, we have 5 different subclasses of basic feature that covers regular features, transitions, right, cover various types of roundings and blends between 2 features, etc. And also have surface, content of the surface. We'll get in more detail. For instance, in the basic feature subtree, we have texture, which would be gears on a gear sheath on a gear, for instance. So it provides information on manufacturing and analysis. So everything that provides information manufacturing analysis would be under this tree. And then under basic feature, we also have holes, would be drilled feature, considered as rotational feature. And so you quickly identify what process categories of holes, through holes, quite intensive. So that's why we need this. Of is made of few subtrees. First one is compound feature. Of pattern for present things that repeat itself. Power important. But as multiple things we have auxiliary geometry of this geometry that rules this geometry, the attributes, and the actual construct of geometry. For instance, what it would look like if we want to define the geometry of this. We define first the type, topology, etc. You can look if you want more detail. But there's also graph that's easier. Case of representation composed of and it basically represents a surface, and each link represents the relation. Each link the adjacent surfaces. And the node itself has a data structure that composes a node identifier, reference to nodes of different adjacent models. And we also need the connectivity of this surface, the information provided here, and everything is tumbled into a shape data structure. So for instance, that's what it would look like with this object. Here we have, for instance, the phase 1 is connected to 2, 3, 4, 5. And the phase 5, for instance, is connected to 4 and 6 and 1. And we also have this part in dotted lines is the inner cylinder. And we see that it's connected to 1 and 6. So that's why it looks like this. And you can get also into more detail if you want to specify this cylinder. It's actually made of tiny plane surfaces that you can represent like this. Also, we define auxiliary geometry. So auxiliary geometry is quite useful when you need to express feature validation tools and to compute feature attribute values. Then we have rules defined by using the nodes we've seen before. Then we have attributes that are useful to express validation conditions for feature recognition. And then we have also geometry. It represents the actual construction of the geometry. So that's what it would look like on the code and the actual 3D model that's represented by this code. That's it. Any questions?
Slide number 16.
16?
There is LOP.
Yes. I suppose it's a synonym of assembly. I'm not sure about this.
What's the question again?
What does lot means?
Lot.
Container.
It's a synonym of assembly.
It means a collection of assemblies.
Oh, maybe.
Container. Part, lot, component. This one, huh?
Yes.
Yes. No explanation.
Yeah. Any other question? Yes.
How does the part and understand what is
because in a part it's made of actual many different shapes that are made up together, and because it's not always a pattern, a part is not always a thing that repeats itself. So you need that separate category for it. And yeah.
So part is similar with
Compound, yes. Yes.
Compound feature is a kind of feature. A part is a kind of content. So to create a part, like a bolt, you need to use many features in sequence. It is a kind of container to include those many several features. Compound feature itself is another feature, complex feature. Well, yeah, it's a concept, specification. Pattern can be another compound feature. You want to separate that because it's for users. It is better to separate them, to have a separate menu. Not so mathematical, practical specification.
Another question? No?
Right?
I just explain a little bit more on frame data structure. This slide is copied from 1 year, 1 semester ago, 1 year ago. There was a what was that? What was the class? Knowledge. Because frame is coming from Lisp. Lisp is a language for artificial intelligence. So they use artificial intelligence. They use frame data structure. Right. But it is simple. It's a kind of table. Frame structure is a kind of table. But they have different names to the slot. Each one is slot or box in a table, so that they can be used as a data structure. They have a frame name and slot name, and then facet and value. It's a pair. Each facet has a value, so it's something like a property. But it's a kind of definition. So this is coming Python data frame. So it is also frame. They are saying data frame. Kind of table. There is a rows, but they need to have different names to make it as data structure. One more slide is coming from Google. They are saying, no, this is slide. NG, New Zealand. New Zealand. R data. Language R. So there's a vector, list, array. Looks similar, right? List, array, vector. And matrix looks like 2D then. And then frame. Similar or different? Can use just here. Hey, there is my a small addition to this. Okay, moving on to my part. Constraint tool. See, this chapter is kind of reviewing previous chapters, but that is more on trying to implementation of previous chapter. So the collection of ideas for the more implementation part. So this section also covers the constraint section. So we already covered this one previously. But they are saying more on implementation. Now, Alexandre covered the previous four. There is a representation, notation, definition, taxonomy, and geometry tools. Same as previous chapters, but it is for implementation now. So you may remind your previous classes, same as constraint tools. So constraint tools in this textbook, the Finland, Helsinki University, they develop a sky blue software and icon app, and they for that purpose they develop a language and constraint, dynamic constraint. Interesting. Right, constraint tools, procedure, parametric modeling has a limitation. When there is a big change, what do you mean by big change? Probably it is topology change. Maybe more than topology change. Anyway, big changes, then procedure, modeling cannot cover this. And EXT design is another from Helsinki University, the professor's name, developer's name. Mantilla was one of the courses of this textbook. IconF is a short name of incremental constraint facility modeling parametric parts. So it's about constraint handling and solution. And this is for short is incremental constraint system. So for the parametric procedural modeling, they use IconF. IconF is for constraint system and system. So it is a sample coming of showing a kind of constraint, geometry constraint. Tangent, concentric, parallel. We already see this similar one in previous chapters. I guess I showed this exact same slide previously. Coming from, I don't know, where is it? AutoCAD something. Parametric concept. Wait, perpendicular, parallel, vertical, tangent, smoothing, collinear, concentric, right. And so sky blue is kind of a constraint representation algorithm. They represent constraint as a method. And architectural constraints is 3 levels. Top level, manipulation functions. Middle level, parsing, understanding the meaning. And conversion into atomic constraint. And lowest level, real constraint and variables and method. Typical, and then constraint types they can handle. Equality, additive, subtractive, unary. This is a very general constraint rather than geometry constraint. Anyway, they need such constraint types. And this is geometric constraint. Younggi, with he surveyed and summarized into. So this one is coming from ISO standard terminology, and this is from CATIA, this is from Siemens NX, this is Cascade of Kite. So he is trying to standardize the terminology, standard set of constraints coming from ISO. We need to such clarification and summarization. And definition language. We need to express different kind of conceptual constraint. We need to have a notation and definition and value and statement. And how can you use main purpose of ICONF, the constraint manipulation software, to support constraint and feature classification. And the feature should always stay on its parent surface. And this is coming in these pictures. See, there is a part with L-block. L-block is, this one is L-block. L-block, and then two crossing slots. This is big slot and another small but deeper slot. Yeah, contacting each other. But we want to make this one. This one is the correct shape. Sometimes the CAD system may mingle around so that the slot goes into the part. So this is not correct. So we want to make a correct one by applying a constraint. So by using constraint, so by using applying they are saying constraining the slot, right? Constrain the slot. But this was not good. So by applying the constraint, this goes correct. That kind of thing ICONF is, or any constraint application system is going on. And dynamic constraint creation, and there is a T-shaped slot and billet. So they want to make a correct shape. So this one block with a slot, T-shaped slot, and then this one should be fit into the correct positioning. Right? So then how can we? It can be a kind of assembly sequence definition for the robots or for the machine. Right? Human can do easily, but machine need process or positioning and orientationing or sequence of action. So how can we constrain them? By using a clear constraint. And here, they need to have a clearance along the neck. Along the neck. They are saying the neck is too thick. So there's a constraint, two constraints. One is for the neck surface clearance, and then the other one is a bottom depth clearance. So that can fit correctly by applying a proper constraint. Alright, case 3, another one, bearing housing cover, and this is external cover and external diameter. The picture. Initial model was not good in design, right? Because the holes are too close to the boundary. So they extend or enlarge the diameter. But this time, the location of those tolerance is good enough, space is enough, but the position is not good. So they move the holes with the positioning constraint. By using positioning constraint, the output looks better, right? I actually included a little bit more slide before, so I will distribute the updated version later. Question? Then we have too much time for discussion. Anyway.
Okay. Good afternoon, everyone. I'm Fahim, and today this is my discussion session. So these are the contents of my discussion. I will talk about 3 topics. The first is BioCAD or CAM applications. The second is convergent modeling. And the third is meshless FEA. So I decided to do BioCAD applications after being inspired by Professor Kim's lecture. And he talked about modeling the bones in the human body. And what I found is that as I was saying, the use of CAD or CAM is actually very prevalent in the dentistry industry, and it is gaining relevance in implant industry as well. So here is one video. Okay.
Today, we will be providing Dexter here with a number 8 CAD-CAM crown. Prior to prepping, the restorative material should be selected based on aesthetics, occlusal forces, and other factors concerning the patient's original occlusion. For Dexter, we'll be using Emax as our restorative material. Number 8 will be prepped to allow for adequate material thickness. While prepping, it is a point of scan. Rotate onto the lingual and work towards and past the prepped tooth. For this video, we will be using PlanScan's E4D software to design our crown. There are generally 3 scans needed. This is the scan of our prep. Here is our opposing scan, and here is the buccal scan of the prep with the patient occluding. Using the buccal scan, we can align the prep scan with the opposing scan to establish a 3-dimensional relationship between the 2 arches. Since we are dealing with the aesthetic zone, scanning from canine to canine will help the eyes when designing the surface before properly seating. A smooth prep with rounded corners will avoid this issue. The design will now be sent to the mill. The Emax block should be firmly secured into the mill in the appropriate orientation indicated in the PlanScan software. Once the crown is done milling, remove the sprue with a handpiece and inject some object fix into the intaglio surface. Place the...
Okay, so after seeing the research based on bone structures like teeth or implants, I thought about the CAD-CAM in sort of non-shielding parts such as organs, and I found that there is some research going on into organic CAD-CAM research.
Mostly of the 3D bioplotter is the flexibility in choice of different materials. Right now, for example, we're printing with silicone. We can work with thermoplastic materials like PLA or polycaprolactone. We can use ceramic materials as well, like hydroxyapatite or tricosyphosphate. Most of these are hard materials that will be used for bone regeneration. In terms of soft tissue, in terms of skin or organ printing, we would be talking about hydrogels. Fibrine, collagen, alginate, these are typical materials that are used by our customers.
So he talks about some materials such as hydrogels or collagen, which is used for printing organic material. I could not find any video like this where they show it being printed, but there is research being done on it. In fact, there is a company called CellProgen, which announced that they are making 3D printed hearts. And apparently that thing is exciting people so much because they believe it will completely change the organ donation process. So my first question is, what do you guys think about the whole BioCAD-CAM industry? Like, what are your thoughts? It's obviously an interesting area of research because conventionally we associate CAD or CAM with mechanical stuff. Yeah.
I think maybe whichever one of us will be working.
Yeah. Or it is something will be working
Because it's going really fast.
I think in BioCAD scanning would be really important because and it will be person specific modeling and
Yeah.
design and manufacturing, it will be expensive as well.
So do you guys think it will mostly be used for making implants and stuff, or do you think organ making or tissue making is also?
I think those could also be implants in some manner.
When I mean implants, I mean more like bone structure, which is currently being studied mostly.
For the organs, you need to have the materials and their bonding, which is very important. The compatibility with other organs.
Maybe complete full organs is still difficult, but maybe a part of the program itself, a part of the organ itself is achievable. Like I think there's research on printing the valve of a heart, 3D printing the valve of a heart. Yeah, so maybe parts of the organ is can be possible.
So I found few pros and cons. These are mostly related to dentistry actually. And for example, normally I once had a tooth replaced, and they first took the mold, and then the tooth was ready in 3 or 4 days. However, if you do 3D printing, then restoration only takes 1 day. Like you immediately scan it, produce it, and then you're able to do it in 1 or 2 hours. So that's an obvious advantage. However, for example, for the tooth replacement, it's not always very accurate. There is this process called electrophoretic deposition, which dentists prefer. So I think the accuracy may be an issue. And also materials is a problem because the 3D printing or additive manufacturing industry still has some material limit problems. So that's it for BioCAD. The second topic is convergent modeling. So this has been defined as a revolutionary game changer. The vice president of Siemens design division has said that this is the biggest change in the modeling, computer-aided design industry since feature-based modeling. So what it does is it completely skips the combining of facets, surfaces, and solids part without any data conversion, and it directly goes to the solid modeling. So I'll show you a video to show an example.
Engineer with Berlin PLM. In this snack bite video, we're going to look at the overview of convergent modeling. There was a lunch bite already created on convergent modeling. In this snack bite video, we're going to look at a quick overview on what is convergent modeling. Convergent modeling works with facets, surfaces, and solids without any conversion. What this means is you can import your STL or scan data into NX as a convergent body and then use your traditional modeling commands such as surfaces and solids without any conversion on the facet. And then we can create geometry directly on or around the facet, and then we can also create and use our Boolean operations as we need on the facet as well. I'm going to create a separate video on the new X11 and the X12. We used the NX and the JT, which then imported, notice it then imports under the non-timestamp geometry, and it imports a facet body. So previous workflows to create a usable model took a long time to actually create a usable model that we can use inside of NX to use our commands. Now in NX11 and NX12, I have a command that quickly does that for me with the convert facet body. So I'll go ahead and select that, select the skull, and then press OK. Now notice in our history tree there,
it converts it into a convergent body, and I can use my traditional modeling commands. So I'll go ahead and create a sketch here.
He does the same for two more examples. One is knee structure, as we saw in our previous lecture, and also for teeth as well. So the advantage, the obvious advantage is that designers no longer have to bother with surfacing at all. And what do you guys think about convergent modeling? Do you think the statement that it's the next best thing since feature-based modeling is true, or?
What is the base of BioCAD?
Base?
Yes,
What do you mean?
like we study feature based, we study parametric. Is it all scanning?
I think, yeah, mostly, like, for example, in the first video I showed you about the dentist, he mentioned that you have to scan it multiple times from different locations. So primarily, yeah, and most of them talk about advantages from the scanning point of view. So I think it's a primary form of making the models.
Because you modify the human CAD models in this video, so I thought that maybe one step is scanning and the other is using something like that.
Yeah, I think the primary
This is
form.
different topic from.
Yeah, this is different.
Convergence model.
Yes, modifying the human
It
CAD.
seems to me that they are starting from imported geometry.
Yes.
Something like that.
Yeah. In both the sets of videos, they mention about scanning imported objects. So I think scanning is the primary form of input. So you guys have any?
It's mostly from scanning that you cannot create something from scratch, but you could design from scratch.
Yes.
Yeah, that's a good point.
From the developer point of view, this is the next question, right? What is the base so that we can manipulate correctly?
Maybe if we have combination of points and we can view them on screen, then maybe we can edit those points. Although that will be a very low level editing, but there could be one.
Yeah. I think what they're trying to take advantage of is the fact that these days the scan and then directly 3D print is increasingly popular, so they're trying to take advantage of that trend.
But in case of 3D printing, you have, for 3D printing, you also have to post-process your geometry to be 3D printing. So with that respect, there may be some problem.
Yeah. So when I check the website, it's only available on NX11 currently. So when I check their website, they gave a list of pros and cons, and they mentioned that it gives designers the flexibility to rapidly create new optimal shapes. So I'm guessing they have some sort of functionality that allows them to start from scratch. Although I didn't find any example video which shows how they do that, but I think they must have one. And they're praising it a lot, but it's NX, so obviously they'll try to present the best side of their product. So it eliminates the time-consuming conversion process, and I think it's best used when it's combined with additive manufacturing. However, like I said, it's only available on single software, which is NX11, and
Is it not available on NX12?
NX11 onwards, so but only on the NX software. So I think that it needs further research, and it should focus a bit outside of additive manufacturing as well.
There must be many internal conversions.
Yeah, probably.
We are saying eliminate time consuming conversion.
Yeah.
Users is okay, but for the internal developers, they need a more conversion.
So the last discussion topic is meshless FEA, which I think is self-explanatory. I'll show this video.
Wong, senior editor for Desktop Engineering magazine. Usually one of the most compute-intensive part of a simulation job is the meshing part, subdividing the geometry into hundreds of thousands of tiny regions or cells so that the software can run equations on each portion. But SimSolid says it can run simulation without meshing the geometry. In other words, there's a meshless approach to simulation. So let's have a look. For a simulation program, SimSolid demands a surprisingly small footprint. The installer, for instance, is only 20 megabyte, and the entire installed program is a mere 40 megabyte. SimSolid is one of the partner products of cloud-hosted CAD program OnShape. So if you have an OnShape account, like I do, you'd be able to grab and use your OnShape CAD projects right inside SimSolid. If you're not using OnShape, on the other hand, SimSolid still lets you import and work with STL files for your design. The program is supposedly meant for assemblies. So what does that mean? Well, here I'm looking at a large assembly, normally defining the assembly joints. How one part connects to another is a manual and time-consuming process. But in SimSolid, the software can automatically scan the geometry, identify the closed surfaces, and add the appropriate connections to the file. SimSolid gives you a number of analysis options. Structural and thermal are included. The workflow is not too different from typical simulation jobs. You define the material for your design, you tell the software where the pressure, the stress, load, or the heat will be, you tell which part of the design is fixed, immovable, then you let the software solve the scenarios to give you an answer. The important thing to note here is the software doesn't take time to mesh your geometry. It simply analyzes your geometry in the background, then run the equations straight on your design geometry. Now, by skipping the geometry meshing, SimSolid is able to also skip the geometry simplification process. This is where you go into your design and remove certain minor features to reduce the time that will be necessary for the software to mesh your design. It's a huge time saver as well. Once the results are ready, you can look at them as stress distribution, heat distribution, or stress plot, and so on.
Okay, and I will show a second short video about stress analysis. This is related to fluid simulation.
Many liquid-dominated flow applications, extremely short turnaround times can be achieved through low pre-processing effort, no meshing, superior solver performance on standard hardware, and superior rendering and visualization capabilities are key characteristics. Water weighting application can cover different driving conditions, amounts of water on the road, any translation and rotation of the vehicle can be combined. The rigid body kinematics is easy to define using the keyframing principle. The user interface is intuitive and easy to learn, enabling the non-CFD experts, such as designers, to adopt the tool. Pre-processing times are low due to reduced requirements for the imported solid components. Kinematics of moving parts can be either predefined or imported. Geometrical variations do not require any effort. Recycling of these scenes is fast and productive. Fluids can be tracked through path lines in order to determine the origin and act accordingly if needed. Visualization and rendering pre-on lab enable users to produce.
So, pre-on lab software isn't commercially available yet, but the SimSolid one is. And so what do you guys think? You guys think meshless is going to be the new method of analysis, or do you think meshing will remain popular? Yes.
How we can define that meshless is the output of meshless is accurate or it is better, because in the case of meshing we can achieve a point when our solution becomes meshing dependent. So how we can say that yes, the solution from meshless method is acceptable?
Okay, so I think we can compare side by side. And even if the output itself is not very different, maybe the process through which it goes. Meshless, one of the main advantages is that it's faster in producing a solution. If you guys have used ANSYS or Console, you know that it takes a pretty long time for the solution to be done because of the meshing. And using meshless may eliminate that step. But I get your point, and I guess it's a pretty young software, so maybe more research will be done on it.
And is SimSolid expensive?
SimSolid, I'm not actually sure about the price. We can check. SimSolid.
$300.
Dimension? 300?
On another website.
Oh, okay. So $300. Okay.
So that we can go side to side, and the superiority is the time, the less time. But there is a lot of research going on the mesh element development. You know.
Yeah.
So if their results are better than this, then how do you justify this?
I guess it's an alternative, maybe. Maybe if someone needs quicker but less accurate results, they can resort to this, I guess. But more accurate results is always desired. But if someone needs a quick solution, they could probably use a program like this.
If we are not looking for accurate results, then we can just simplify the geometry and do it by hand.
Yeah,
there is no point in doing simulations.
Anyone else has an opinion?
What do they use instead of mesh?
He mentions in the video that they use geometry, but I'm not sure how they use the geometry to create, to determine the analysis. Because, but the results are pretty fast, so I'm not exactly sure how they can expect to be accurate without meshing. They don't describe in their videos or their website how they determine the geometry without using meshing. So.
I think there is a limitation. Kind of geometry.
Yeah, it's a possibility. Yeah. Okay, so another advantage that they mentioned is that it doesn't require as much coding as mesh involved software such as ANSYS or Console would require. But it seems kind of strange, but maybe they're right. So currently there's only one commercial software, which is SimSolid. So that's it. Thank you for. Just inspirational quote from one of the programmers of JavaScript. He says that progress comes from finding a better way to do things. Don't be afraid of innovation. So these are the references, and thank you for listening.
Good or long discussion. About the mesh list, you may find many journal papers on mesh list. And it is a long history, rather long. You can find many. Another one is in CFD. So this one is for FDM, right? There is a many general papers, but in CFD we don't have a mesh. Instead, they have a grid. Because water is moving, you cannot make a mesh. So CFD is different. Water is flowing, so that you only have a static grid. And there is another area called particle method. This is also different. Similar to the water particle, you can use, they are saying you can use for the structure tool. Interesting
alternatives.
arrays. Okay, see you on Wednesday.